Welcome to our introduction to network switches. Now, it's fair to say that although an absolutely essential part of all IT infrastructures, network switches are for the most part hidden away, whether that's under your desk, in wiring closets, or mounted in rack cabinets in the server room or data center. But they are there, connecting every single device directly or indirectly, handling every email that you send, every video that you watch, and every file that you save in the workplace. Every desktop PC, workstation, server and printer in your workplace will be connected to a switch. Each laptop or phone you use to connect in the office works via a wireless access point, ultimately connected to a switch. And any CCTV your premises may have also connected to a switch. And this is key because switches not only ensure the vital connections are made between systems, data and people in an organisation, they also run protocols and processes that govern how fast connections are made, what security is applied, and what happens if anything goes wrong. This network connected together by switches is referred to as a LAN or local area network. So although we said switches are used to connect everything together, not all the switches are equal in their functionality. They all direct data traffic between users, but the type of data being shared will have an impact on the type of switch best suited to the job. In a small network where the users are typically sharing email and accessing small files on the server, then an unmanaged switch will suffice. As the name suggests, there's no management of data within the switch, it simply sends and receives data when requested. Now imagine one of the users wants to do a Zoom or Teams call. If the video and sound data from that call was randomly interspersed with emails and file access, then the quality of the call would be very poor. In this instance, a smart switch should be used. The term smart implies that some intelligence is employed in how the switch manages the flow of data. Simply put, any voice or video data is prioritised over files and emails, so that call quality is guaranteed. The Teams user has a great call and the other users don't even realise that their emails have been delayed by fractions of a second. This feature is referred to as quality of service or QoS. As a network scales with more users, more devices and larger data sets, a greater degree of management is required to stop bottlenecks occurring. Quality of service is applied across all voice and video communication as standard, but other methods of segregation can also be used. A customer service team may use Zoom and Teams, but otherwise only really enter data into a CRM tool, whereas a marketing department will also video call each other, plus also access large files and create content that's much more demanding on their network connections. On top of features like QoS, a fully managed switch allows the creation of virtual LANs or VLANs, where an entire work group such as the marketing team can be prioritised over other users if their demands are more critical. Fully managed switches also allow rules to be created for each switch port or group of ports, so users can only have access to certain systems or just the internet if they're guest users. The more complex and larger a network, the more management is required, so you only tend to see unmanaged and smart switches in smaller businesses. Now, having covered traffic prioritisation and management, it is worth pointing out that no matter how much segregation and priorities you apply, the speed of the network connection must be able to handle the type of applications being used too. So now let's take a look at network speeds. Ethernet is by far the most common standard when it comes to network communication. It's been around since the early 1980s, and over this time the speeds of available Ethernet connections has vastly increased. The initial commonly available switches were capable of 10 megabits per second, followed by 100 megabits per second and then gigabit Ethernet, which provides 1 gigabit per second. And this is now the most common standard in home and small office networks, with many larger businesses now having up to 40 gigabit speeds. In the high-performance computing space, where complex scientific research and analysis is carried out, a rival standard to Ethernet was developed in the 1990s, and this was called InfiniBand. Although an InfiniBand switch works in a similar way to an Ethernet switch to transfer data, InfiniBand achieved improved throughputs by needing less host resource to control data transmission, enabling increased throughput and reduced latency. Like Ethernet, there have been several generations of InfiniBand, starting with SDR, standing for Single Data Rate, providing 2.5 gigabits per second. This has since been superseded by Dual Data Rate, or DDR, at 5 gigabits per second. Then we've got Quad Data Rate, or QDR, at 10 gigabits per second, 14 data rate at 14 gigabits per second, enhanced data rate EDR at 25 gigabits per second, high data rate or HDR at 50 gigabits per second, and the latest next data rate or NDR at 100 gigabits per second cards. Now, however, since InfiniBand cable has 3 possible types that dictate the overall throughput, either a 1x, 4x or 12x cable, the number referring to the physical links within the cable. The 4x cable is the most common, and when used with the latest NDR interface offers speeds of up to 400 gigabits per second. Although InfiniBand dominated the HPC space for decades, Ethernet has since now matched its capabilities and now progresses on a similar scale at speeds of 100, 200 and 400 gigabits per second, with similar levels of reduced latency too. Now, before we get into the types of ports, it's worth a quick mention as to the number of ports any switch may have. Switches start as small as 5 ports, but these are designed usually for the home user. Usually 12 ports is the minimum that you'll see in a business, scaling to 24 and 48 port units, all taking up a single rack unit or 1U form factor. These numbers generally refer to the number of standard Ethernet ports. You'll sometimes also see 28 and 52 port switches with an additional SFP Plus or QSFP uplink ports. In the case of InfiniBand and high-end Ethernet switches, only QSFP ports will be present, so the 12, 16 or 32 port number refers only to that type. As network speeds have increased, the type of ports and cables required to carry these speeds has also evolved. Initially, copper cables using RJ45 ports were used at Ethernet speeds of up to 10 gigabits per second. Then fibre optic cables took over from 10 gigabit per second speeds upwards, using SFP interfaces standing for small form factor pluggable. This allowed most tasks to be carried out at 1 gigabits per second, but offered faster uplink ports at 10 gigabits per second. The SFP ports on any given Ethernet or InfiniBand network switch are designed to take a variety of SFP modules, called a transceiver, each intended to provide a guaranteed throughput speed over a specified distance, from meters to many kilometers. The latest SFP Plus transceivers are available in SFP multi-mode and single-mode options to cover distances up to 160 kilometers. QSFP transceivers are 4-channel versions of SFPs and are available like SFPs in a number of versions. Rather than being limited to one connectivity medium, QSFPs can transmit Ethernet or InfiniBand. The original QSFP transceiver specified 4 channels carrying 1 gigabit per second Ethernet or 5 gigabits per second InfiniBand. QSFP Plus is an evolution of QSFP to support 4 channels carrying 10 gigabits per second Ethernet or InfiniBand. The QSFP28 standard is designed to carry 100 gigabits per second Ethernet or InfiniBand, and finally QSFP56 is designed to carry Ethernet or InfiniBand at speeds of 200 gigabits per second. So now we understand that as networks grow in complexity and demand from more users, mixed media applications and larger files, a higher degree of management will be deployed across numerous high bandwidth switches. However, the more mission critical work that the network of switches is supporting, the more vital it is that they're not susceptible to overload or failure, as the communication across the network would cease. To combat this, several types of redundancy are used. Firstly, devices such as servers, storage and other switches will often have 2 rather than 1 cable connecting them. This offers an instant failover should one cable fail. It also allows for a greater bandwidth and load balancing across the 2 connections. Secondly, and very similar to what we saw in our introductory guide to servers, the fans and power supplies in managed switch are normally hot swappable, making these types of switch less likely to fail due to a single component failure. And finally, entire switches can be made to be redundant. If you think back to our work group scenario, it may be that the sales floor of an organisation contains 200 people all needing a network connection. This will require multiple switches, even using dense 48-port versions, so we have an option to use stacking switches. Stacking or stackable switches have a dedicated stacking port that allows a daisy chain connection between up to 8 units, allowing them to be seen as a single entity, but also to fail over to each other should a failure occur that removes a whole switch from the stack. Within most Ethernet networks are numerous devices such as wireless access ports and IP cameras that have the ability to draw their power directly from the network port rather than their own dedicated power supply. This makes positioning cabling simpler. For example, if you want to place a camera on the outside of a building, this is made much easier if you don't need a plug socket for it nearby. Another example are IP phones, where the phone connects to the network switch and then subsequently connects the user's PC via a small 2-port switch embedded in the phone. Receiving power directly from the switch port is known as Power over Ethernet, or PoE, and it's a feature on many switches, whether unmanaged, smart or fully managed. Naturally, with more phones and voice video traffic, it's wise to use QoS and perhaps VLANs, so PoE is most often used by businesses on higher end switches. The amount of power that can be provided depends on the uprated power supplies within the switch, some being able to provide power to some ports, others lower power across more ports, and the highest spec ones high power across every port. A PoE capable switch will be rated in one of the following 4 categories that you can see on screen now as to what consistent power it can provide. So there you have it, you've now got a good grasp of network switches, their types, uses and capabilities. For further information, we've added links to our more in-depth network switch buyer's guide in the description below for you. We hope you found this video useful. If you've got any questions at all or feedback, please pop them in the comments section below and our network experts will reply to you when they can.